Hi there everyone, welcome to the video lecture series on double integration. In this video lecture I shall be continuing with the discussion of formulation of double integration with different types of region. Alright, in our previous video lecture we had seen a type 1 region. Let us see one more example on similar lines. Let us take up this semicircular region. Here we are given a semicircle with radius a. Alright, now as we can see, this semicircle is on the upper part of the xy plane or above the x-axis. So the equation of the semicircle we had already seen, it is of the form y equals to square root of a square minus x square. We had discussed regarding this type of semicircles and their equations in our previous video lecture. Alright, so now we have to understand whether it is a type 1 region or a type 2 region. In order to detect whether it is type 1 or type 2, let us pass a line passing through the region in a vertical direction. Alright, so when this line is passed, it is entering the region on x-axis, alright, and it is exiting the region at the semicircular region. So we shall show that entry point by this red dot, alright, and the exit point by this blue dot. Now we had also noted down a very important fact in the theory, that the entry point of the line and the exit point of the line must remain the same throughout the region. Okay, when it is passing through the region, the entry point and the exit point must remain the same. So let me support that thought or that point that we had noted down with the help of the animation over here. Now let us see. Here the animation helps us to understand that the red dot remains on the straight line and the blue dot is traveling on the semicircular path. So what is important here to note that they both remain all throughout on the same path. They are not changing their path. So that means that the entry point and the exit point remain the same. That's the main important thing. Now this animation is the most important thing according to me for a student to understand, because this is the intuitive aspect of double integration that is required by the student to grasp. Okay, so when you are solving the questions related to double integration, an imaginative skill is required regarding the same. So this is one point where you need to imagine this movement of the vertical line that we draw across the region. Alright, okay, so let us write down. So the vertical line enters the region at x-axis and its equation is y equals to 0. It is exiting at the semicircle, so the equation is going to be y equals to square root of a square minus x square. Okay, now having understood that this is the type 1 region, we shall write that it is type 1. Now in order to find the projection, it is evident from the diagram itself that the projection is on the x-axis and it's from minus a to a, right? So here let us write down that. So the projection are going to be from minus a to a. Okay, now the double integral, when we are writing, let us see how to write down. The double integral is going to have a general function, because the function right now is not mentioned and given to us. Because it is type 1 region, here we are going to have that dy dx as the order. Okay, and now let us write down the limits. For the limits of the y are going to be from y equals to 0 to y equals to square root of a square minus x square. So instead of writing that entire equation, I'll just write square root of a square minus x square as an advanced version. Okay, now the projection limits, as I told you in my previous video lecture, that they are going to be x equals to minus a to a. So outer limits are always the projection limits. They are minus a to a. Okay, so here we are ready with our double integral for this semicircular region. Okay, now let us move further and see a different type of a region for a type 2. Here we are given this kind of a region, okay, a triangle in which the equations of both the two sides are given and one intersection point is given to us, and some things are labeled upon the x-axis. Okay, so now in order to find the double integral for this region, let us first pass a horizontal line across the region. Note that we are passing a horizontal line. Now when we pass a horizontal line, what do we observe? It is entering at y equals to x and it is exiting at x equals to 2 minus y. Now we also have to check that all throughout the entry point and the exit point remains the same. Now see the intuitiveness, it is very much similar to the previous example, it's analogous, but now the movement is going to be from bottom to top, okay, and the similar animation will be running, but this animation we have to grasp it and it is going to be intuitive in nature. So you have to remember at the back of your mind that similar kind of imagination should run in our mind too. So let us see. So the point to note is that the red dot and the blue dot always remain on the same sides, or the equations on which they belong to, they don't change. So do you see that they are remaining, the red dot remains on y equals to x and the blue remains on x equals to 2 minus y. Okay, so the entry point and the exit point do not change. Okay, so this is what I mean. So let us write down. The line enters the region at y equals to x, and so that y equals to x is same as x equals to y. Okay, now the line is going to exit at x equals to 2 minus y. Okay, now in order to have the projection, yeah, so this we are claiming as type 2, but to have the projection, let us see how to see the projection. Projection for type 2 region is on y-axis. Okay, so and it's going to be from 0 to 1. Now let us see how it is from 0 to 1. Can you see that the intersection point given to us is 1 comma 1 over here? Now having understood that, now that's the apex of this mountain kind of figure in front of us, the triangle. So it's the maximum point for this triangle, and so when I take a shadow of this entire region on the y-axis, it will maximum go from origin to 1. Alright, so let us see the shadow. See, this is how the shadow will go. Let me rerun that. This is the maximum shadow that you can have. Now so the shadow is going to go from 0 to 1. Okay, so this projection we have to understand. That's one more animation again. So again an intuitive way, but if you understand this properly, you can write down the projection limits clearly. Now let us write down the double integral for the same. So the double integral now is going to have again a general function, but the order is going to change because it is type 2. Since it is type 2, you will have dx dy instead of dy dx. Okay, now the innermost integral will have limits of x. So the entry point is going to be x equals to y. Okay, so that's the x equals to y over there. So at the lower limit is x equals to y, and the upper limit will be the exit point, so that is going to be x equals to 2 minus y. Okay, and the projection limits are going to be for y. Okay, so the outer integral will have the projection limits, and they are y equals to 0 to y equals to 1. Okay, this same integral, if it appears to be lot cluttered or too many components, you can simplify this, and it's rather not simplifying, it's just a simpler way of writing the same thing. You just write it as outer limits as 0 to 1 and the inner limits as y to 2 minus y with the order dx dy. Okay, so this was the type 2 integral. Okay, type 2 region and dx dy as the integral order. Now let us go for one more example on type 2. Now here we see a much different figure in front of us. We have a circle whose equation is given to us as x square plus y square equals to 10, and here you have a parabola whose equation is y square equals to 9x. Okay, and this is the shaded region given to us. Now as the lectures series moves further, the regions will become more different and complicated, and more equations will be involved in it. So there are certain things to remember, that whenever a geometrical figure is given to us, first of all note down their equations. Okay, so we note down the equations that y square equals to 9x and x square plus y square equals to 10 is given to us. After that, if any intersection points are there, find out those, or any simpler properties that you can understand or deduce from the given equations, note down them in the diagram itself. So now from the diagram I can immediately note down that the equation of the circle is given to us x square plus y square equals to 10. So on x-axis I can immediately plot down the radius. It's going to be r equals to square root of 10, right? Radius is going to be square root of 10, so I put down a point on x-axis that r is root 10 comma 0. Now here there is this point, as we can see, the intersection of the circle and the parabola. So let us first find the intersection. Now it is not necessary that all the diagrams will have intersection points, but if there are any intersection points, we need to find them. So let us find the intersection points here. I can see that there is this one intersection here up, and there is one at the down, and we need the upper one, so we shall use that. Okay, so in order to find the intersection point here, as you see, x square plus y square equals to 10 is given to us, and y square is 9x, so we shall substitute y square as 9x and simplify. So when I put y square as 9x, I can see that this becomes a quadratic. So when I solve this quadratic, x square plus 9x minus 10 equals to 0, I get the following factors. Okay, so x equals to 1 and x equals to minus 10. Now x equals to minus 10 is not required here, so I work only over x equals to 1. Now when x is equals to 1, I shall substitute in this parabolic equation, so y square equals to 9x. Okay, so when I substitute it over here, I'll get y square equals to 9, and that would give me y equals to plus minus 3, and on substitution I can get two points over here, that is a as 1 comma 3 and b as 1 comma minus 3. So I label them on the diagram, a as 1 comma 3 and b as 1 comma minus 3. Now I don't need the bottom region, so I'll avoid that for discussion. What now shall we do? Now see here, we pass a horizontal line across the region. Okay, yeah, we can also label the region here as I have labeled here. I'll tell you how to label. It is OARO I am labeling. So the region labeling we can do, always keep it as a closed region. Generally students just label OAR. It's not a good practice. Keep it as a closed region, because double integration and the further topics will need a closed region, but later on it becomes evident from the concept. Okay, now pass a horizontal line across the region. What do we see? That the line enters the equation y square equals to 9x. Okay, you can see that it is the red dot over here. Okay, and it can be written as x equals to y square over 9. Okay, now the line is going to exit the circle. Okay, x square plus y square equals to 10 at the blue dot. Now always remember, whenever the circles are considered into the picture, you try to understand them even with the help of the semicircle. Now if you observe carefully, this is a semicircular region. Also a part of a semicircle is the arc is belonging to a part of a semicircle too, and moreover, it is on the positive side of the x-axis, right? The exit point, the blue dot, is lying on the circular arc which is a part of the semicircle, and it is on the a positive side of the x-axis. So when I want to write in terms of x alone, so I have an option. So x square plus y square equals to 10. I can write it as x equals to square root of 10 minus y square. I have taken positive square root instead of negative. The reason is x is always positive in the right hand side of the y-axis. Okay, you can observe over here, so x is positive, so that's the reason here we have avoided the minus sign. Okay, so here the line is exiting at x equals to square root of 10 minus y square. Okay, so this is the main thing over here to remember. Now further, let us see how to calculate this projection. I am mentioning over here that projection is from 0 to 3 and the limits are going to be y equals to 0 to y equals to 3. So let us see how. Here the highest point of the region can be seen as a1 comma 3. Alright, so the shadow of the region will fall upon the y-axis. Okay, so what are we going to get is that when we drop a perpendicular, or when we take the shadow or the projection of the region on y-axis, we will see that it will fall on 0 to 3. Okay, so let us see here how to write the integral now. So now that means that we have also calculated the limits as well as the projection, so our claim should be clear that this is the type 2 region. So this is the type 2 region because we have passed a horizontal line and we are able to see it. Okay, now so let us write the double integral. While writing the double integral, we have to again remember, since a function is not given, here we are writing the general function f of x comma y, and its order is going to be dx dy. So the innermost integral will have the limits of x. They are going to be the variable limits. So the lower limit is going to be x equals to y square over 9, and the upper limit is going to be the exit point, the blue point, that was at x equals to square root of 10 minus y square. So that will come as the upper limit. Okay, and here y equals to 0 to y equals to 3 are the projection limits, so they will be there as the outer limits in the double integral. Okay, so here our integral is ready, the double integral. Alright, so I hope you are able to follow this concept because it has a imaginative skill involved. Okay, and there is some procedure. All this material of writing that you see on the screen can be slowly reduced, but initially we will write down all, and later on once we master the skill of writing the double integral, only the diagram and the double integral will matter, and a few calculations. Okay, not much. All this theory will vanish, it will already be absorbed in our brain. Okay, now I shall take up more examples in the coming video lectures. Till then, keep solving good amount of mathematics. Thank you.